We're ready to continue again. I'm Joe Graziano, the director of the Columbia University Superfund Research Program, and it's my great pleasure to introduce our next speaker, Ana Navas Acien. Ana has worked in the metals field for many, many years. We've known each other for many, many years, and we are thrilled that we were able to recruit Ana from Johns Hopkins to join us at Columbia as of last June, and she's made her presence known in very many ways already. And today she's going to present some of her thoughts and work in progress. This is Ana's real interest is on arsenic and other metals at the low levels of exposure, and she's going to talk about exposure assessment challenges and possible solutions.
So thank you, Joe, and for the introduction. It's a real pleasure to be here. I remember 3 years back, I was here, I just came to give a talk. And it's really wonderful to now be here as a member of Columbia University. And yes, there are many challenges when we are trying to do arsenic research at low levels of exposure, especially from the exposure assessment. But epidemiologically, it's very important. These are important questions. So we need to think of possible strategies, and we've been thinking for a number of years. So I'll present some of those, and then also at the end, I would like to discuss with you some of the work that we want to pursue in the future, and also maybe to get some feedback from you. So just to summarize what we know from the health effects of arsenic, we all know that it's a poison at acute exposure levels, at high levels. We know that it's through chronic exposure at relatively high levels, especially from drinking water, but from other sources too, like medications, arsenic medications, or others, like chronic exposure of arsenic, is going to result in very well-known health effects, cancer, cardiovascular disease, etc. The evidence between 10 and 100 micrograms per liter, I would say, has been increasing quite substantially in the last decade. And for instance, in the Hills cohort was extremely important in providing evidence at those exposure levels. And also some of the work that we did in the Strong Heart study has provided information, as I'll show a little bit more, above 10. But very few studies have actually addressed what's happening at levels below 10 micrograms per liter in drinking water. This is important because the standard has actually changed. Also because it's changing in some places, like New Jersey has a 5 microgram per liter standard. The Netherlands is actually going to have a standard of 1 microgram per liter. So what's happening at these low levels, we don't really know right now. And the other important issue when the arsenic levels in the drinking water are low is that then food really becomes a very predominant source of exposure. And right now, I would say we don't know what are the chronic health effect implications of those exposures through the food. So just to show some example of this research that we now have right now and how difficult those studies are to let us know what's happening at below 10, I am going to present some results from this study that we did in the Strong Heart study looking at arsenic and cardiovascular disease. And if you look at this exposure response, dose response curves, between urine arsenic exposure, and it's a microgram per gram of creatinine, but in our population, dividing by creatinine is like dividing by 1. So in a way, the exposure range you could think is equivalent to microgram per liter. So you can see that if you look at all cardiovascular disease mortality, above 12.2, you could argue a little bit below, probably above 10 micrograms per liter, the increased risk is actually statistically significant because the confidence intervals are clearly above 1. Below, here you have 7.4, here you have below 5. There is a lot of uncertainty in the exposure response. And the confidence intervals are wide, and actually for CVD mortality, it looks pretty linear. For coronary heart disease mortality, it looks like there is a threshold. It's flat, then it goes up. But the confidence intervals are very wide. So we don't really know what's happening at these low levels. There is a question? Yes?
Why do the confidence
This is the reason that they cross is because we are setting the reference at that level. So it's 1. You see, so it's a 10th percentile, so that's why they cross. Good. So, okay, diet. So we don't know what's happening below 10. Diet is really important. Rice, any products that have rice products in them, like brown rice syrup and things like that, granola bars, apple juice, chicken. We showed recently that before of the banning of the roxarsone and naltrexone by the FDA, actually chicken intake has been a meaningful source of exposure also, relatively small, but also detectable to arsenic in the US population. So this is important, and we currently don't know what's happening. The major challenge is the exposure assessment. And first of all, because at these low exposure levels, they need to integrate multiple exposure sources, including food, but also even the water, whatever the levels are. If you are exposed at 2 or 3 micrograms per liter, that's likely to be relevant. Even air, if there is arsenic in the air pollution, dust, soil, children playing with soil, etc. So the exposure assessment is going to become much more complicated. So biomarkers are really essential. So urine arsenic is generally a well-established biomarker of arsenic exposure. It's useful in addition to study metabolism, what is very important from the susceptibility perspective. The main challenge that we have, I would say we have 2 challenges. One is the organic arsenic as from seafood, and I am really going to focus on that challenge quite a bit during this talk. The other challenge is the correction for urine dilution that I am going to set that aside for today. Then the other biomarker that we have is the toenail arsenic that mostly reflects toenail inorganic arsenic species, because the inorganic arsenic species are the ones that grow with the toenail that you can actually detect. The limitation is that we cannot really assess arsenic metabolism, and the other main limitation is that toenail growth is actually very important, and we don't really know well the determinants of toenail growth and how that really interferes with our exposure assessment. But I am going to focus mostly on urine arsenic because that's been one of the most well-established biomarkers. And I am going to discuss how seafood is such a big challenge. Let's start with a very simple scenario where we are exposed mostly through drinking water. The inorganic arsenic is methylated in the body, and the 3 major species, the inorganic, the MMA, and the DMA, contribute to total urine arsenic. And we generally use the sum of the 3 as our biomarker of arsenic exposure. So that's pretty straightforward. That's what we generally do. In the Strongheart study, people don't eat seafood, so that's great. We can do it in Bangladesh, etc. That's the case scenario. When we come to more general populations, that's not going to work out so well. First of all, we have all the other sources of arsenic from the food. The inorganic arsenic, so that's okay. The inorganic arsenic will be methylated, that's fine. The other foods, for instance, rice also contains DMA. So that means that, okay, this DMA is slightly different than the DMA that came originally from inorganic arsenic. DMA is also a toxic species, but it's not the same to reflect DMA directly with its own toxicity that a DMA that originally reflected inorganic arsenic exposure. Because that inorganic going through MMA to then DMA might have a very different toxicity than just DMA per se that came from the rice. So that's the first challenge that I am even going to skip that, because then we can, let's imagine we can, in general populations such as the US, we'll study inorganic MMA and DMA with some DMA coming directly from rice as our biomarker of exposure. That's important. Let's try to understand the health effects of that exposure. But let's think now of the complications of seafood. Okay, generally it's been very well accepted that seafood contains very high levels of arsenobutane that contribute to total urine arsenic. But we've also learned, I would say in the last 10, 15, 20 years, but not actually more, probably more like 15 years, that the arsenosugars and arsenolipids are very important in seafood, and they have a very complex metabolism because part of them, they are methylated, they go into DMA that also contributes to the total arsenic in the urine, and then they have many other metabolites that are very actually challenging to measure in the lab. So let's see a little scenario here of an experiment that was done with people eating 16 mussels. They were all restricted from eating seafood for 3 days. And look at what happened. At the beginning, at the baseline time, before eating the mussels, they just have in their urine DMA and arsenate. They measure the two together, or they plot them the two together. I'm not sure why. And but most of it you can imagine is DMA from whatever their inorganic, their arsenic exposure background is. After 3 hours after the mussels, they have quite a bit of arsenobutane, and then they start showing DMA, it's increasing, and other unknown species, and half of a day later, that becomes even more dramatic. So this is showing that you have arsenobutane and you have these others coming from the arsenosugars and the arsenolipids. There is an interesting volunteer that, even though had 3 days of seafood restriction, that is generally what is done in most classical studies, to ask people to restrict eating seafood, this person still had a lot of arsenobutane in their baseline urine. Maybe he didn't comply, but actually what seems to be the case is that this person is a chronic seafood eater. He would eat seafood like 3 times a day or at least once a day. So he's a typical Spanish person. Like if you think of Spanish, you have at least for lunch or dinner or tapas in the middle of the day, there is a chance that you eat seafood at least once or more a day. So that's again going to complicate exposure assessment a lot, even if you ask people to restrict seafood. And then the same kind of happens, DMA increases, et cetera, and the other organica. So this is if you give people mussels that have arsenosugars, and then also arsenobutane, a very complex seafood arsenicals in seafood. What if you give people 1 milligram of arsenosugars? So this is 2 volunteers, and again, their patterns of metabolites over time. The most interesting thing to observe is that the majority, both in these 2 volunteers, is DMA, is a major metabolite. It's at least around half in general of the metabolites from the arsenosugars is DMA. The other interesting thing with arsenosugars that, again, I am going to discard from the thinking of epidemiological questions right now, but for the future it might be interesting, is that the metabolism and the excretion patterns are very different. One volunteer only excreted 15% of the initial dose, while the other one excreted 88%. So that's a lot of variability. And why? That's not clear. So now I am going to move from this experiment into a national database, national study, the NHANES study. And that has done some arsenic biomonitoring with some challenges because the inorganic and the MMA species are mostly undetectable. So we can focus on the arsenobutane, total arsenic, and DMA. That are the species that are adequately measured in NHANES. What you can see is that arsenobutane is a major driver of total arsenic levels in the US population. If you, at levels above 1 micrograms per liter of arsenobutane, practically all of the total arsenic in the urine is arsenobutane. It's just the rest is overwhelmed because the contribution is so huge that you cannot, the variability becomes lower and lower. The total arsenic variability decreases dramatically because it's overwhelmed by how important arsenobutane is. At low levels, below 1 micrograms per liter, it's actually good. You can see the variability that you can imagine comes from exposed to inorganic arsenic or maybe from DMA in the rice, et cetera, all these other sources that are not seafood. So the people with the lower arsenobutane levels might be people that we can actually assess arsenic exposure not derived from seafood. Above 1, it looks really bad. And actually arsenobutane correlates pretty well with DMA also. And why is that happening? Is because if you go back to the figure, arsenobutane has a common source with DMA through seafood and the metabolites or the arsenosugars and the arsenolipids. Arsenobutane serves as a surrogate of seafood arsenicals in general, not just itself, because as you saw, eating mussels give you both. So that's why there is this correlation, but that also means that when you study DMA in NHANES, you are not just looking at inorganic arsenic exposure or not even DMA from rice. You are actually looking quite a bit at seafood arsenicals, basically. So even when people have done, you can look at NHANES papers, and the main typical strategy is to subtract arsenobutane from total arsenic. You say, okay, if I take total arsenic and I have subtract arsenobutane, I am going to have the arsenic that is not from seafood. But that's actually not correct. If that was true, this correlation would disappear. It would be totally flat. But the correlation remains quite important. So again, subtracting arsenobutane is not sufficient to remove the seafood arsenicals. Okay, so here this is NHANES and levels of total arsenic, DMA, arsenobutane, and total arsenic minus arsenobutane by different seafood that people reported eating in the last 24 hours. You can see that if you ate sushi or mollusk, your levels of DMA are quite high. That's because there is a lot of arsenosugars in those seafood products. But in any type of food that you eat, you can see how DMA goes up. The same for arsenobutane, the same for total arsenic, the same for those. So we need to start thinking of what else can be done if we really want to do arsenic research at low levels. Otherwise, it's going to be very challenging as our DMA is actually reflecting in large part seafood arsenic. So it was kind of depressing when the first time I noticed that actually this problem was before Thanksgiving in 2007, when NHANES first released their data. And they did it just before the day Thanksgiving. And I started looking very excited. I had worked a lot with NHANES, and I knew the arsenic was going to be released. So you can imagine, I felt like so excited to have this data. I was probably one of the first person like diving into the data. And when I looked first at low limits of detection, I was like, wow, this is terrible. Second, I saw these correlations, and I was just like, okay, let me go for Thanksgiving celebrations. This is not good. We are not going to solve this in a day. But we've been thinking hard with colleagues, students, and we thought, okay, can we maybe re-estimate arsenic concentrations that are not derived from seafood by estimating urine arsenic, regressing it on arsenobutane, using arsenobutane as the surrogate of seafood arsenicals in general, and not just arsenobutane itself. Then we can extract the model residuals, and these model residuals now are really independent of arsenobutane and other seafood arsenicals that arsenobutane serves as a surrogate for. The advantage of using arsenobutane is that it's specific to seafood. It's an objective biomarker of seafood, actually, what is very interesting from the nutrition perspective. It's not metabolized into other species, and it reflects these other seafood arsenicals. So this is generally what we think arsenobutane relates to total urine arsenic, but now it's, through this backdoor pathway, so it's going backward, it's reflecting seafood intake, and now it can help us remove the contribution of not only arsenobutane itself, but also of these other arsenicals. If we come here, by adjusting for arsenobutane or by regressing the arsenicals on arsenobutane, we'll be able to make this regression line parallel to arsenobutane. If we go to the model and now we take the residuals, imagine this is the regression line. This is with a restricted cubic spline model, but imagine this was a linear regression model with a regression line. And you took all the residuals now would be totally independent from arsenobutane itself and the other seafood arsenicals that arsenobutane reflects. So, yes?
How absolutely can you rule out arsenobutane transformation? When you saw the muscle sort of experiment?
Because people, I think that's very well known that arsenobutane is not metabolized in the body. The muscles themselves have arsenobutane. So that's why the muscles have a complex group of arsenicals, so they have arsenosugars. Arsenosugars are not metabolized into arsenobutane.
But that you can say that?
Yes, for sure. You know that from the other experiment that I showed you. Arsenic never shows up. Yeah, that I think is very well known. Yeah. But okay, we had this idea, and then we thought, let's try to test if this works or not. So Miranda Jones, who was a student working with me, and she was working with MESA on air pollution, but she knew MESA really well. She's now an assistant professor at Johns Hopkins. We worked together and to try to do a pilot study within MESA. So MESA is a multi-ethnic study of atherosclerosis. It recruited more than 6,000 participants in 6 cities around the US. The nice thing is that they have white, black, Hispanic, and Chinese participants. And we used 300 participants for our pilot to try to see if we could actually use MESA to do research at low, moderate levels of arsenic. And the first thing for us was to deal with the seafood problem. So this is the method that we use. As I mentioned, we are regressing each arsenical, inorganic, MMA, and DMA. We are regressing them on arsenobutane. Then we are extracting the residuals. And now then we are kind of calibrating or calculating a new measure for each person by giving them the mean levels of people who have very low arsenobutane levels, so that we have a new estimate of inorganic, MMA, and DMA for that participant. And to test the hypothesis, we compare the association of the original biomarker versus seafood intake, and also with N-3 fatty acids that are very well known from markers of seafood intake, because there are specific fatty acids from seafood. Yes?
That second point about adding
the residue, yeah.
to the mean levels, what's that for?
Yes, so sorry, let me go back here. If you just take the residuals, you just have, let me try to do it with a mouse. If you take the residuals, that's the difference between the mean and the actual level for each person. So that value is meaningless from a unit perspective. So then to have it meaningful value, you need to add back the mean. But if you add back the mean, then you get back the original value. If what you've done is actually you've replaced the seafood arsenicals by arsenic that would not be coming from seafood. But that would not tell you the levels of exposure from the population. So in order to have levels of arsenic relevant for the population, what we did is just to add the mean inorganic, the mean MMA, and the mean DMA from the people who were eating very low seafood, the people who are below less than 1, you know? So now you have like a mean value for the whole population for inorganic MMA and DMA that should reflect what people have been exposed to if they have not had seafood arsenicals. We can discuss more if it's not clear. Okay, so our hypothesis is that our newly estimated biomarker would remain associated with rice intake, as rice is a source of inorganic and DMA, but would no longer be associated with self-reported seafood intake, as we've effectively removed that contribution. Okay, to do that, we did the arsenic speciation. The analysis were done, or the analysis for the pilot were done at Grass University. And one little thing that we've done is, because at very low levels, it can be challenging to measure the arsenite and arsenate in everybody. And so what we did is that we oxidized the urine samples before analysis. And so you can see now it's much easier to detect the arsenate. So arsenate is going to reflect the whole inorganic exposure to inorganic arsenic, and not just levels of inorganic arsenic, and not just the arsenate percent. So in this table, now we have the measured concentration originally and the calibrated or the estimated concentration. So you can see that after correcting for seafood arsenicals, the sum of the species, the inorganic MMA and DMA, has decreased dramatically from 8.1 to 3.1. The reason, because we've removed, hopefully, those seafood arsenicals. DMA also has reduced substantially. We've also removed a little bit and reduced MMA and inorganic. And that's, I think, is the toll that we have to pay because seafood arsenicals also have a little bit of inorganic and a little bit of MMA. So ideally, we would want to know their health effects too, but it's going to be very challenging because they are really overwhelmed by all the organic arsenicals. So that's a little bit the toll that we are paying. But you can see with the percentage of the species how DMA percentage has now decreased and the other species have increased. And that's because basically what we've done with our method is remove DMA that was derived from the seafood arsenicals. We also use NHANES to prove the method, but I am not going to present that because of time. So let's now see if the method is working. And this is try to compare to self-reported seafood intake. So these are our levels of DMA and the sum of the inorganic MMA and DMA species by self-reported seafood intake, with the reference category being the people who eat seafood less than once a month. These are the never or very rarely eating seafood, and then increasing categories. And we are using, we are modeling in the log scale the arsenic, and then we are exponentiating the coefficients to give you the relative difference. So those who eat between 2 and 4 times, they have 27% higher DMA and 93% higher DMA as compared to those who eat very rarely. You can see that our estimated biomarker, those relationships are totally gone. So that kind of shows that the method worked well and that we were able to remove the contribution of seafood arsenicals. If you did the same with the total arsenic minus arsenobutane, this will not work. And self-reported intake would still be related to total arsenic minus arsenobutane because you are not effectively removing. So now, this is with then minus 3 fatty acids. I am going to skip it because of the time, but it kind of shows the same thing. And now I'm going to show you what happens with rice. So, okay, rice is a major contributor to arsenic, likely to be in this population. And you can see how higher intake of rice is related to higher DMA levels. And the estimated biomarker, the association still remains quite substantial. So our biomarker adequately reflects inorganic arsenic exposure. You can see that the ratios are a little bit lower. That could be related to 2 scenarios. And one of them is that people who eat rice are also likely to eat seafood. There is this common pattern of kind of, I would say, maybe healthier eating. And people, instead of eating French fries, would eat rice with seafood instead of eating a hamburger with fries. And so part of the rice associations that we could see in studies that do not of rice that do not adequately control for seafood might be overestimated. So that could be one part. The other part could be that maybe we are over-adjusting and over-correcting. So that's also possible. Still, the relationships remain strong. So it suggests that our estimated biomarker is adequate to reflect inorganic exposure, arsenic exposure, and DMA exposure from rice. So the arsenic estimated biomarker provides an assessment of exposure that no longer reflects seafood intake, and this method can facilitate research about low-level arsenic exposure in general populations with seafood intake. So now I want to show you a little bit how we've used the biomarker to look at the differences in exposure levels by race, by city of origin, by race and by city. Those are the 2 factors. So you can see that in MESA, Chinese Americans, even after adjusting by city, let's imagine there were differences in arsenic levels in air pollution in the different cities. So if you look at model 2, after adjusting by city, Chinese Americans have 84% higher arsenic levels in their urine as compared to whites. And Hispanics have 45% higher. Blacks and whites are similar. When you adjust for frequency of rice intake, the associations remain very strong. There is a small attenuation. You would hope that that attenuation would disappear because rice would explain the difference by race. So you need to remember that seafood questionnaires are terrible, food frequency questionnaires are terrible. So it's very difficult to really quantify exposure. So I think the race differences might still be reflecting pretty much differences in rice intake. but maybe there are other sources that we don't know. But my guess would be it's mostly rice. Let's now look at the differences by city. So here we use, these are the 6 cities of the study, and Winston-Salem is our reference category. If you look at the model 2, that is already adjusted by race, because there are not all the racial groups were recruited in all the cities, so that's important to look at model 2. You can see that both, before adjusting by race, New York, Chicago, and Los Angeles had higher arsenic levels. After adjusting by race, the difference kind of go away, suggesting that it's because we had recruited more Hispanics and Chinese Americans in those cities. There's still, you need to remember the study is very small, only 300 participants. Both New York and Los Angeles did have 15% higher levels as compared to the other cities. So that, I mean, could be interesting to try to understand. We've actually found an association with air pollution, with PM2.5 concentrations, with higher PM2.5 being related to higher arsenic. But we need to try to understand that more. And then the final model is, after adjusting for rice intake, is kind of similar to the previous model, a small attenuation, but not enough. So these are relative concentrations with ratios of geometric means, but people generally want to know the levels of arsenic, no? So that's why we present here in the figures the adjusted geometric means, and we do it for each racial group in all the cities. And you can see that the places and racial groups with the highest levels are Hispanics and Chinese, the Hispanics from New York, actually, who are most likely to be from the Caribbean, Puerto Rico and the Dominican Republic, and the Chinese from Los Angeles and Chicago. And in whites, you can see the highest levels are from Los Angeles and St. Paul, Minnesota. In blacks, the highest levels are in Los Angeles. So actually, Los Angeles tends to show higher levels in almost all the racial groups. What is interesting, even is more in the western side, maybe there is some water arsenic there that could be contributing. So in summary, for the findings that we have so far from MESA, we can say that seafood is a major contributor to urine arsenic in this population, in this multi-ethnic population from 6 US cities. Arsenic not derived from seafood could be estimated by using this residual-based strategy using arsenobutane. The overestimated arsenic levels were higher with rice intake. The estimated arsenic levels were higher in Chinese and Hispanic Americans compared to white and black participants in MESA. The Chinese participants from LA and Chicago and the Hispanics from New York had the highest exposure levels to arsenic. And within white participants, the levels were higher in LA, in St. Paul, and within blacks, higher in LA. So this study, hopefully also it's a small study, but also helps us think a little bit about some of the research and public health needs. And I think one of them is that really we have a terrible surveillance system for arsenic at low levels. And if we think of lead as to compare another environmental chemical that is very important, we have actually a pretty good system for surveillance and monitoring of lead. And NHANES, for instance, has helped us very importantly to track trends of lead exposure over time. We have systems for lead poisoning around cities. I think for arsenic, that is a very, very important environmental chemical. Currently, we don't really have a good biomonitoring system in the United States. And there is no information on geographical and race ethnic differences in exposure levels. And NHANES, unfortunately, is very limited right now because of the limitations in the undetectable species. The laboratory methods, unfortunately, are not sensitive enough. And so that's something that we are trying actually to work with. Annie is not here today, but Annie Nigra, but she's very interested, and we are trying to see if we can address some of those issues in NHANES. And then finally, from the researcher's perspective in terms of health effects, this is clearly there is a great need for moving this research forward, and MESA can be a very good, interesting study because of the diverse geography and the diverse ethnic groups. So I want now to finish kind of the talk. I wanted to tell you a little bit about MESA, what MESA has measured. So MESA is funded by NHLBI, It has also been funded in part by the EPA for air pollution assessment. It's an extraordinarily rich study. They recruited 6,000 participants, 45 to 74 years of age. They've been examined 5 times. The 6th exam is coming this year, and you can look at the assessment. For cardiovascular disease, it's actually on parallel. For lung disease, it's on parallel. They've used their chest CT scans and their to be able to have extremely good information on pulmonary imaging, cardiovascular coronary calcification. They have cardiac MRIs, they have functional information on how the heart works. I mean, this is the best study of cardiovascular disease ongoing right now. They've published more than 1,000 papers. They've published in New England Journal of Medicine, Nature, Science, all the big journals. And it's extremely rich study, and they've measured a large amount of biomarkers are already available, genetic data, etc. So what they don't have is arsenic in everybody. They actually have very limited, I would say, environmental information except the air pollution. That's been very well characterized. But potentially, this study provides an opportunity to better assess arsenic exposure. Doing the pilot was extremely important because first we had to show that actually we could assess exposure in the population. This study is very restrictive, and they are very careful how they invest their money, and most important, how they invest their biospecimens. These biospecimens are extremely precious, so they are not going to measure it on a biomarker that is not well established or well validated. So that's why we actually have been working so hard to try to show that this can actually work. And we are now pending approval, but we already got the first set of comments. We've responded, so I believe we will be approved to do it. So the hypothesis that we would like to focus on for the main research, since the study main focus of MESA was cardiovascular disease, atherosclerosis, we think that the best way to go is to continue, and that's also been an interest of mine over the years, to continue with those hypotheses for the main grant, but of course this provides an enormous opportunities to look at other things, like Tiffany is very interested in the lung outcomes, so hopefully we can continue, we can do this research with many other multiple health outcomes. So first we thought it's important to look at the association and understand what is the relation between arsenic levels at less than 10 micrograms per liter. We went very quickly, but if you look, the median in the population is 3.3, and the interquartile range goes up to near 6, and the range is actually the maximum levels after you correct for the seafood is around 9, 10. So the majority of the population is actually below 10 micrograms per liter in the urine. So we want to look at these relationships with clinical cardiovascular disease and also atherosclerosis clinically measured. Then we believe it's important to look at susceptibility and effect modification. This might be very important at these low levels. Maybe there is not an effect overall, but maybe there are certain subgroups based on smoking status or based on the genetics that where this arsenic might be more important. So the second aim would be modification. Yeah.
So your first line is arsenic exposure, water arsenic. You mean urine arsenic?
No, it's urine arsenic, but what I am thinking is arsenic exposure in populations exposed to arsenic in the water less than 10. That's what the sentence kind of means, but maybe that's not clear. So, you know, the idea is arsenic exposure, like urine arsenic levels less than 10, but reflecting the effects of arsenic in populations that are exposed to levels in the water less than 10.
So I think I'm trying to understand the drug too. So in some senses, you don't really care where the arsenic comes from.
Exactly. Yeah. You don't care where it's coming from. Yes. I think the difference is that most of the previous research has generally been done in populations exposed to levels in the water, where water was the major driver. And when water is the major driver, except maybe in Bangladesh, because the rice and the water combination is a cocktail that is really dramatic. But in places where you don't have this high rice intake, the water is the major driver if you have arsenic in the water. And then, these levels of arsenic from food, etc., they are very minor compared to the water. So, but when you don't have water arsenic, then, but again, if you have water arsenic at 5, that's important. We want to know that.
Yeah. Strictly speaking, as written,
yes,
you cannot test that hypothesis.
Oh, I would say we can, because all the people were recruited from Baltimore, Chicago, Bangladesh, LA. All of these communities are below 10. So then I would say we can say that. We don't have a water sample, unfortunately.
Yeah.
And that will be important because some, for instance, in LA, I was thinking it's interesting that the Black Americans in LA have higher levels than the white Americans. So why is that? Where are they living in LA? Who maybe is having groundwater? Or, I mean, I think in LA, groundwater is still very important. So.
LA water is high. Historically, at between 10 and 15, also very recent, right?
Yes.
And they still might have I have to look at it. That they
yes.
need the 10, but they're just not one.
Yes.
You look at it.
Yeah. So I think that's what this is showing a little bit, So that having a water sample would be ideal. So something that's actually possible because they are going to go into a new exam. So we could try to collect a sample of water from the MESA participants. That could be possible.
There's also a lot of variation locally that each community doesn't necessarily get their water
from the same
LA aqueduct.
Yes, especially because these cities are very large. So yeah, there could be. Arsenic is at Minnesota is an arsenic high spot. We saw in the whites in Minnesota they were relatively high. Yeah. And the last hypothesis is taking advantage of the rich data information. We can actually look at the mechanistic pathways potentially for cardiovascular disease, and to look a little bit more to have an idea with this figure from a study that review that we put together a couple of years ago. So this is the main aim, to look at the association with the clinical outcomes and with the atherosclerosis outcomes, but then to try to look at the different mechanistic pathways, so hypertension, diabetes, electrocardiographic abnormalities, of oxidation and inflammation, etc. So those would be the idea for the study. And just before taking the questions, the acknowledgement, really this is the work with the imputation and the modeling that Miranda Jones did and her experience with MESA. Maria Telles Plaza also helped a lot with the statistical model, and then Maria Grau, I want to acknowledge her with always helping us, having these amazing, beautiful figures. It's really great to have a team of people thinking very hard to make this work possible. The communities and the participants, we didn't really have funding to do this study, but you're always looking for something under the stone, like something you can pull some money here and there to move the science forward that you think is important, not necessarily that one that is funded. And I also wanted to show this picture at the end. This is from the ISCE meeting in Rome, where we went many of my students and trainees, past trainees, with work in arsenic, and really it's great to get all these ideas and thinking together. This is really what makes the science possible. So thank you, and please more questions and comments if we have still a few minutes, and it's possible. Thank you.
Sure, go right ahead.
So this is from Mirek Ciblo at UNC Chapel Hill.
Yes.
In our mouse studies, arsenic,
inorganic
arsenic from water appears to be metabolized differently than inorganic arsenic from diet. Methylation rate, tissue retention, etc. Do you see similar differences in population studies?
Okay, so that's a very interesting question, but I don't think we have an answer for that, because unfortunately, we don't have a tracking signal that tells us, hi, I am inorganic arsenic from water, or hi, I am inorganic arsenic from food. So, or I am MMA from water or from food, or DMA from water or from food, so that the day we could have that analytically, that would be, or maybe it exists. And Brian is going to, Benjamin is going to tell.
Before we leave that,
yeah.
Could we ask Mirek what his explanation is for that?
So I think in human studies, we have not been able to assess that. And in animal studies, I am not sure why.
So one of the things that comes to mind is I used to be at Dartmouth, and Josh Hamilton used to do these studies where he would show that there was a nutrient-like response at the lowest levels. I was thinking of his rat studies where he had to he spent several years designing mouse chow that would be low enough in arsenic to even be able to do the experiment. It's really hard to remove enough of the arsenic from the food to actually see the low exposure levels in these experiments. And maybe, I mean, that seems like it's actually related here in some respects. It's hard to know. It gets hard to measure, especially in these foods.
When you had the water from the low levels in the water and then the food arsenic in the chow for the animals would be overwhelming those levels. But if they are behaving differently metabolically, I mean, honestly, what does that mean in terms of toxicity? Yes, how can it be? I mean, the only thing you could think, if it's kind of bounded differently, you know, like, I don't know, like in the food, it's likely to be more complex. And while in the water, we know it's very well dissolved and it's very hydrophilic. So maybe the way it goes through the membranes and the pathways, it's different. And that's why it will be metabolized differently. That's the only explanation that I can think of. We know already that the absorption is different. Like in the food, the absorption is, I don't know, 20% or so, but when in the water, it's almost practically 100%. So that, yes?
I mean, I guess it's an interesting question. When you get to low enough level that you will actually find benefit?
That's a very difficult question to answer. And I would say, you know, right now, I think the question from Jan was if at these very low levels, could we see any benefit from arsenic? So right now, I would say we don't have any evidence to suggest benefit. So I would say right now, with the evidence that we have today, my answer would be no. I would expect either null associations or a small increased risk. I would not necessarily expect a benefit. But, you know, the science of arsenic is very complex. We have many hypotheses that show up with in different ways than we think. So I would not bet for that not to happen either.
Mirek just commented, could be effects of matrix.
The matrix, yes. Yeah, I was thinking the microbiome maybe also, since the gut microbiome might be influencing the arsenic in the food and the water differently. So that could influence metabolism also potentially.
Any other questions? If not, thank you to both of our speakers. This was an enjoyable session. Thank you.
Thank you.